So what have we been talking about? So the last few classes were about volume. Today, what we're going to discuss is two other sort of geometrical ideas that turn out to be very important. One is called arc length, and the other is called surface area. What's fascinating is both of these sort of geometrical questions, and you might be more familiar with surface area than arc length right now. Perhaps you were in elementary geometry and you guys talked about things like you have a box, you know, you have 6 sides, you know, what is the area, the surface area of your box? Maybe you memorized formulas for the surface area of a sphere. An idea you're probably not too familiar with yet is what we call arc length. And that is we're going to try to understand or assign a measurement to a curve. Now, you would imagine if you put your brain into work right now that would be important. If you've ever been on an airplane, I think you understand that when you're flying somewhere, you're not flying necessarily in a straight line because we're flying over the surface of the Earth, which means we're flying in a curved direction. You might also, maybe some of you go to the park and you run or you walk, and maybe you use one of those apps that maps how far you've ran and how long it took you. And you're not running necessarily in straight lines. And so how do we assign distance to curved sort of journeys? Or a better way for that, a better way to say that is some sort of trajectory. If I walk out of this building right now and then I walk down the road, down to the main road, Babcock, then I walk, I mean, how far have I walked? How do I incorporate, for example, elevation into my travel? And so arc length is sort of the thing that helps us do that. And then what's even more surprising is the types of, as you would imagine, arc length and surface area are going to be described through integrals. And what they do is they open up this whole new world of advanced mathematics. Now, we're not going to do that in here, but the types of integrals that you find when you compute arc length and surface area form a very important class of integrals that we study in advanced mathematics, and they're used in all types of areas. One that you might be at least not, I don't want to say familiar with, but understand is the idea of encryption. So in a digital world, we use very fancy, I don't want to say fancy, but some of it's fancy, mathematics to keep communication secure, passwords and bank accounts and all that. And some of the ways we do that are connected to this stuff, as are many other problems. So the stuff we're going to talk about today can really open up a bunch of doors, not just the length of curves and the surface area of a three-dimensional object, as it were. Okay, so let's sort of set the stage for how we want to go about doing this. So I ought to switch colors. I like the idea. So in elementary classes or in elementary courses, we define the length of a line segment in the plane using what's called the distance formula, but it's really the Pythagorean theorem. So just a little reminder of what I mean by that. So if I were to draw a coordinate system, and let's say this is my XY axis, I might have a point over here, and then I might have some point over here. And so let's connect them with a line segment. I don't want that, I want a different color. So remember, we have to give names to these points. So perhaps we'll call this point down here x sub 1 comma y sub 1, and we might call this point x sub 2 comma y sub 2. And then the length of the segment is equal to the square root of x sub 1 minus x sub 2 quantity squared plus y sub 1 minus y sub 2 quantity squared. This was often in your algebra books, they would call this the distance formula. But where this formula comes from is you just take this segment and make a right triangle. Yeah. Say that again? Oh, the previous page? Sure. I'm sorry. My apologies. You gotta yell louder next time. Be the voice. Having fun? Did you have a good weekend? Drink more White Claws? No. Or Trolleys or whatever? Why? We good? All right, cool. So, okay. So here's the new problem. What if we had a curve? And I'm going to put the word curve in parentheses because we really haven't, we use it in a very colloquial way all the time, a curve. But what if we had a curve? So let me just, for the sake of argument, take the pink marker and ask, what is the length of this? So what's the length of the pink curve? So does everybody understand the problem? Now, what's very cool about this, and I've done this in the past, I've actually like gone to schools and worked with like middle school kids on this and high school kids. And it's cool because everybody kind of uses their intuition and jumps to conclusions real quick, which is okay. We're not mad about that. But if I said to you guys, I said, take 10 minutes and think about how you would find the length of that curve, at least one of you would say, well, here's what I would do. I'd go get a piece of string, and I'd lay the string on the pink curve, then I'd pull the string and lay it next to a ruler, and that's how long it is. And I would say, that's great. Very good. Now, how the hell are you going to do that when we're flying a space shuttle to the moon? Are you going to put a string at the back of a space shuttle and hold on for dear life until it gets to the moon, and then they'll release it, we'll wind it in, and then we'll lay it next to a big ruler somewhere and figure out how long our flight path is, right? So again, it's in some ways, this is an easy problem to state, but it turns out it's not an easy problem to solve. Why is the microphone zapping when I ain't even using them? When in doubt, mute them. Can you guys still hear me in La La Land? Hopefully, I think they can, because I'm not using that. I'm using my computer's microphone. I love this. Someone's going to answer. My favorite. Oh, there it is. Ethan, how are you? Ethan already told me he was going to cheat on Friday by using Wolfram to do all his homework. That was fun though. Like, I didn't know you guys didn't know all about that stuff. I thought that was common knowledge. Let me get my scissor. We good? Okay, so again, let's emphasize. It's an easy question to sort of state. How long is that that pink curve? But really, we think it's easy intuitively, but it turns out it's not. It's actually quite a difficult problem to do. So what we're going to do in this class is we're going to state it. We're going to state it in a very simple case, and then some of you will take Calculus 3 and you'll learn about it in a more general case. But the idea is very similar to what we've been doing though. We're going to take our curve, chop it into small pieces, look at one of those small pieces and say, hey, we can approximate it by something. And then we're going to add up all those little approximations and we're going to get a Riemann sum. And we know that Riemann sums are lovely because instead of taking n to be a number, we can let n go to infinity. We can take a limit. And when that limit happens, by definition, we obtain an integral. And integrals are nice many times, not all the times, but many times they're nice because we can readily evaluate them. So here's what we want to do. We need to come up with a definition of the length of a curve so that when we give it a straight line, it gives us this formula back. Does that make sense? Let me repeat that. We need to define what it means for the length of a curve so that if our curve happens to just be a straight line, we get the intuitive notion in the original line we learned about as a kid. Now that's no different than how the Riemann sums were used to compute area. Think about how we motivated the integral. We said we want to have a notion of area of a plane region. And we want this notion to tell us the size of curved regions, but we also want it to be so that if we give it a rectangle, we get the original formula, length times width back. Does that make sense? Hopefully. It's a law, very overwhelming. Okay, so let's get to it. Where'd my pen go? So in Calc 2, we study this problem in the simplest case. And that is the curve is the graph of a function y equals f of x. So y is dependent on x in some way. Now, why do I make note of this? Why am I telling you this is the way we're studying it? Well, if I go back to the previous page, one thing you'll note if you paid any attention in your algebra classes is that that pink curve down there ain't the graph of a function because it fails the old vertical line test. Now, that scenario, like with that pink curve, we cover that possibly at the end of this term, but absolutely in Calc 3. But we can't jump that far yet. We want to talk about the simplest case so far, right? And then later on, we build to more realistic versions. We've done that with area too. Think about the regions that we've studied. Every region that you know how to compute the area of either has one curved boundary or two, right? The only regions we studied were those whose boundaries were the graph of a function. So it's going to turn out even more, and this is just a technical detail, but it's important to state. In fact, we will restrict ourselves to functions that not only have a derivative, but their derivatives are continuous. So this is just a technicality, but it's an important one. because the formula that we're going to see is the proper formula only works if this is the case. Does anybody want to say anything? I mean, again, and by the way, you don't have to really worry about that last sentence ever again in your life, but I have to tell you that because it's technically true. And you'll see why. Actually, I alluded to you at the end of class. In the formula, you have f prime, right? Well, if f prime doesn't exist, that formula doesn't make any sense. And if f prime is not continuous, then we don't even know that you can integrate it. So, sort of like we're watching our backs. Okay, so here's the idea. And we're going to do this in depth. We're going to do it in depth for the line, or excuse me, the arc length. And then we're not going to do it in depth again for the surface area because it's almost identical. So, but again, I'm going to emphasize this. I did this when we spent all that time on the pyramid problem. I can't emphasize that you think about why we're going to do it the long way once in all these cases, and I'd really hope that you ponder the theme here, how we're going to do it. So here's how we do it. So here's the plan. And this is very similar to how we did volume. Here's the plan. 1, cut up the curve into little pieces. We'll call them little with, it's relative. And then the next thing we'll do is we'll approximate each piece with a straight line. Now this seems completely reasonable. I mean, think about this. We've talked about this before, both in Calc 2 and in Calc 1. Take any curve you'd like. I don't care. Zoom in on a small enough piece, it starts to look like it's what? A straight line. Find any curve. You're sitting on one right now, the Earth. When you walk across the room, do you feel like you're walking along a curve? No, right? Because we are so small relative to the size of the Earth that for all intents and purposes, it's flat. And another way of thinking about that is take any curve. You can approximate it with a tangent line at any point. We talk about that in Calc 1. So really, curves that are differentiable, or curves that you're familiar with seeing, in fact, if you zoom in enough on them, they become straight lines. Let me beat this dead horse one more time, because I think it's important to do. So you guys should all be seeing my internet. So let's go to Desmos. If you're not seeing Desmos, yell, but I think you're all seeing it. Let's just say y squared. That is a curve. No one's going to argue that's a curve, right? But if I start zooming in on it and zooming in on it and zooming in on it, I don't care where I pick, eventually it's going to start to look like a straight line. For example, we know that's a curve, but if someone walked in this room right now and they said, no, that's a line, it'd be hard to argue them unless you showed them the formula, right? Zoom in more. Zoom in more. I mean, no one's going to sit here and argue that that's not a straight line. It looks like a straight line to us. I mean, now here, I'll hide this. That's a straight line. So if I zoom in enough, it looks like a straight line. Now, of course, if I zoom back out, hey, we have parabola. And you would imagine that up here more, you don't have to zoom in as much because it's more straight to begin with. And in fact, there's a way that we can measure the idea of how much curve there is. It's called curvature. And maybe you've seen, I mean, you've definitely felt this before. If you ever rode an amusement ride or been on a highway and you go too fast on a sharp turn, you feel your body. Your body senses that certain curves put more force on your body at the same speed. Right? So we can quantify all that. Some of you get to do that in physics and calculus. The point is, curves, if you zoom in on them, you can approximate them with straight lines. So I don't think anybody's going to disagree with that. All right, good. All right, so once we approximate each piece with a straight line, we approximate the whole curve with all the straight lines. And luckily, if we do this creatively enough, this sum of these straight lines is a Riemann sum. And so and then once we have a Riemann sum, send n to infinity to get an integral. So that's sort of the theme that we've done numerous times in this class. And we'll do it again. And many of you will get to do it in other courses too, whether it's a physics class, maybe it's a chemistry course. Yes. Sure. I need water anyhow. While it's on my mind, did you ever fill out the major form thing yet, or no? That's because I didn't send it to you. Trick question. Good. All right. So let's sort of draw what this might look like in a particular sort of generic case. So imagine I have my XY axis. Let's draw some curve. Now, let's imagine also we have 2 points on this curve. We have A and let's say B. So what I might do is I just might chop this up into some, pieces. And so what I'll do is I'll connect these dots. With straight lines. So let's say I don't want to use pink, I'll use red. So if I put this from here to here, and then from here to here, and then and so if we wanted to describe this with some fancy words, we could say blue curve and a red polygonal line. And so where the curve is not too steep, the red is almost identical with the blue. And where the curve is a little more quote unquote sharp, where we see that it's not perfect. But if I were to increase the number of pieces, then all my air goes away. So what we're going to do is we're going to zoom in on one of these pieces and we're going to see how it goes. So let's label these guys. You might remember that this is like x sub 1. We'll put a dot here. So this would be like x sub 1, x sub 2. This would be 3, 4, 5, 6, 7. Let's look at x sub 8 to x sub 9. So on the next page, we're going to zoom in on this piece. So maybe what I'll do is I'll highlight that with a circle here. So that's what we're going to do. We're going to zoom in on this piece. Now, we're just going to zoom in on this piece. But, I mean, what I'm going to do would apply to any piece, whether it's x sub 1 to x sub 2, x sub 5 to x sub 6, whether it's x sub k, comma, x sub k plus 1. It can work on any one. Does anybody have a question about this? Okay, so let's do that. On the next page, I'm just going to draw my blue. So on that piece, my blue kind of looked like this, right? I think. Let's just go back and double check. Yeah, that's close enough. That's good. And then I have my piece here and my piece here. And then down here, my x-axis is down here. So I'll kind of illustrate that. So this would be the point x sub what? X sub 8. This would be the point x sub 9. We can get real specific. This is x sub 8, comma, f evaluated at x sub 8. That's scary looking. And then this is the point x sub 9, comma, f evaluated at x sub 9. And then all I want to do is I want to connect these two dots with my red line like we said we were going to. So all I'm interested in is this piece. Does anybody have a question about this? Now, to make things a little easier, what we're going to do is we're going to label some things. We're going to give things some names. And it's very helpful if we just use our intuition of geometry too. So what I'd like to do is I would like to draw a right triangle. So I'm going to draw a horizontal line here, and I'm going to draw a vertical line here. This is a right triangle. And I'm going to note that this guy is a specific distance. And this guy is a specific distance. Now, we always give this guy a name. This guy is always called dx. That's what we've been calling this guy since Calc 1. Anytime we break our interval up, we always call that distance dx. That's what we've been doing. And then for simplicity, I'm going to call this distance dy. So let's make sure everybody understands what these things are. So notice dx is equal to x sub 9 minus x sub 8. And what is d sub y? D sub y by definition, the way I'm denoting it is f evaluated at x sub 8, or excuse me, x sub 9 minus f evaluated at x sub 8. That's the distance between the top and bottom. So that might take a moment for us to come to grips with, but hopefully you will. So let's give some names to some other stuff. So let L sub 1, L sub 9. Why am I going to call it L sub 9? I'm calling it L sub 9 because I'm thinking of this as the 9th piece. Does that make sense? So if I go back, I have my first piece goes to x1, my next piece x2, x3. So I'm thinking of this as x sub 9. Or excuse me, the 9th piece of my polygonal line. So I'm going to call that L sub 9, L sub 9 equals the length of the blue curve between the 2 points. And then note that that means, by the Pythagorean theorem, what is L sub 9 equal to? L sub 9, we can't say what it's equal to, but we definitely know it's approximately the length of the red line. So it's definitely approximately, what is the length of the red line? Well, that is the square root of delta x squared. So we'll write it like this, plus delta y quantity squared. That is nothing more than the Pythagorean theorem. So that's a very important piece. So what we're telling you right now is the length of that blue curve from the first point to the second point is approximately the length of that red line. So that means if L is the whole curve's length, it would be approximately all the pieces put together. So that's an important thing we need to come to terms with. So again, if one piece is approximately this red line, then if we add up all the red lines, we'd imagine when we add all those up, we approximately get the full length of the curve. That seems intuitive, I think, right? So you might want to go back to that picture. If I add up all those red lines, what I should get, in this case, I would be taking 11 lines. I should get an approximate length of that blue curve. Okay, so let's write that down. So thus, if L equals the length of the curve, then L should be approximately the sum of L sub k's, where k goes from, say, 1 to any number n you want to go to. Maybe we go to 10, maybe go to 11, maybe we go to 1,000. So I have a question about this so far. Again, if you want my opinion, maybe you don't. In my opinion, this is way more important than be able to compute integrals. This is understanding what's happening, understanding the engineering of it all, the science behind it, in many ways, the genius behind it. We have software to compute the integrals or approximate them. What we need humans to do is figure this kind of stuff out. And hell, it only took us thousands of years to get to it. So, and we're asking you to learn it in a couple weeks. Okay, so here's the thing. We can definitely approximate. What this is saying is it says we can approximate any curve we want using a polygonal approximation. That's fine. But that could be very tedious. I mean, you don't want to do that by hand. And by the way, to this point, this idea of approximating a curve would work for any curve, even one that wasn't the graph of a function. But in order to get the integral to pop out of here, we're going to have to really, what I like to say, massage this L sub k, this square root thing. Because right now we don't have a Riemann sum. We have to make it, well, we do, but it's not obvious what it is right now. We have to make it look like a Riemann sum. And some of you might be sitting there saying right now, what does he keep saying Riemann sum? Well, remember, Riemann sum means function evaluated at a point in our, what we call our partition, times delta x. We need a sum of that. We need something times delta x summed from 1 to n. That is a Riemann sum. We don't have that right now. At least not the way it's written. We have to get it. So first off, this is still a good way of approximating things. If you are good at a computer, you can easily write simple code to do this for you. And there's lots of software already that will do this for you. If you go to GeoGebra, you can do this. In fact, maybe I'll show you this. Let's show you. I've written one of these before. Now I just have to remember my password. Well, I should be logged in. All right, sign in. Good. So one of the things I did for you, my legends, many moons ago, was to do this. So here is sort of what I'd like you to pay attention to is don't worry about all the crap on the left, all this stuff over here. Worry only about the picture for now. So imagine for a second I have this curve f of x, which is the square root of 1 minus x squared. And I want to approximate it with a polygonal line. So if I do my standard, you'll notice right here my d of x, which is b minus a over n. We've been doing that the whole time, equal lengths. You'll notice if I do 4 lines, I get, this is not a very good approximation. I mean, look at the picture. The blue is not doing a good job of approximating the green. And the length of the blue lines, if I add all 4 of them up, I get 3.03. You can see that down here. But now what happens is if I increase the number of straight lines I add, if my partition is now larger, say I now have 8, well, now you see that I'm not good down here. I have a gap here, but up here, I'm pretty good up here. And so what happens is I increase the number of lines I use to say, I don't know, let's say I go up to 17 or 18. Now you'll notice that my air is slowly going away. And what we see is as n increases, as the number of my lines increases, my polygon starts to represent that semicircle. And what's even more nice is if you look down here, the length of my polygonal line is what? You're starting to notice it's something that's familiar to you. We expect it to be what? Well, this is a circle, or excuse me, a semicircle of radius 1. And we know that if we traverse the whole thing, its circumference, we believe, if we believe our middle school and high school teachers, is 2 pi r. So it should be 2 pi. But I'm only doing half of it. I have a semicircle. So the length around this circle, if we believe our high school teachers, is pi. And in fact, that's what this is telling us. That's what we're getting. As I increase this number, the larger n is, the closer this is going to get to 3.14. Does that make sense? So we see it visually. Perhaps we do this if you want. Is it going to let me? Won't let me do it. I don't think I can edit this. How can I not edit it? I made this stupid thing. Oh, well. It's not letting me edit it. Okay, no big deal. I think you get the point, though. Someone have a question? Straight line, indeed. So this is sort of the idea. Okay, so here's what we want to do then. We want to figure out the computer. We know the computer can do the approximation part. If you just learn the proper code on GeoGebra, you can do this part. But what we'd like to do, if possible, is get an exact formula. We clearly saw a limit happening there. 3.0, 3.0, blah, blah, 3.1. So it's going to keep getting, and it's going to get closer and closer to pi, 3.14159. Okay, so here's the important part now. So it remains to show that this sum let me be a little more careful. I think I wrote something down wrong. Let me go back. Yeah, let me be careful. What I wrote here, let's fix this. This is technically not correct. L is actually, yeah, so the way I should have written this is as follows. I sort of cheated. So let me fix this. I should not have written L sub K there. This should be this scary looking formula. That's what I should have written there. Sorry about that. Okay, so what it remains to show is oh, that ain't good. It remains to show that this guy is in fact a Riemann sum. So there's a couple ways to sort of do this. One way is to go back to the picture and use what we call differentials and think about that this red line is approximately the tangent line. That's one way of doing it. Like if you drew a tangent line, or in fact, not even that, if you used them, you could think about the mean value theorem. And so that's what we're actually going to do. So we're going to draw the picture again. And this time I'm just going to draw a few pieces of it. So here's my sort of my curve. And this can be any piece. It doesn't necessarily have to be the 9th piece or the kth piece. This works for any piece. And let's sort of put our triangle in here. And remember, this distance is delta x. This distance is delta y. And what happens is the mean value theorem is something we talk about in Calculus 1. And what it does is it gives us a very simple way of rewriting an expression for the red line. So what I'm going to do is get this pink out here. And what I'm going to remind you of is the following. There is this pink line here. Or excuse me, this pink point, I should say. So let me get a different color. How about, we'll just use. So I'm going to call this point, C sub k, comma, f evaluated at C sub k. Now you might not be sure why I'm calling it C right now, but that's because you don't remember the mean value theorem. And so what I'm going to do is draw a line. And here's the key observation. So the slope of the red line is dy over dx. That's elementary algebra right there. Change in y over change in x. The slope of the purple line is f prime evaluated at C sub k. So what that means is the mean value theorem says that this is true. Guarantees there exists a C sub k, so we'll write it very carefully. This C sub k has to be between X sub k. Now, right now you're probably going to be getting confused, but you got to remember we have now used these X sub k's consistently since calculus 1. So this C sub k has to be between these two guys. So for example, if k is 9, C sub 9 has to be between X sub 8 and X sub 9. So if what I mean by that is if you go back to one of the previous pictures, C sub k would be in here somewhere. Or excuse me, C sub 9 would be in here somewhere. So the mean value theorem guarantees there exists this C sub k with the following. You have f evaluated at X sub k minus f evaluated at X sub k minus 1 has to equal f prime evaluated at C sub k times delta x. But what is this? This creature right here, we've already given it a name. It's called delta y. So I can rewrite this in a very nice way, which agrees with the picture I've drawn on the left. I can say that f prime C sub k is equal to delta y over delta x, if I just do some algebra. So right now, it sort of seems like maybe we're kind of going, I don't want to say circles, that's a bad way, but it seems like maybe we're just writing things down and they don't really have sort of any, there's nothing we can gain from them. But that's actually not true. So the one thing to note is that purple line and the red line have the same slope. That's what we're saying. And we're not just saying it because I drew it that way. We're saying it's theoretically true by the mean value theorem. Now, even if you don't remember what the mean value theorem says, that's okay. We've at least logically verified it in theory. So what this means, though, is we're going to be able to rewrite this blue sum. That's where we're headed. We're going to be able to take this creature and rewrite it in a way that a Riemann sum pops out. And the reason I'm drawing all this is because if you take the time to go back and work through this, maybe 2, maybe 3, 4 times, what you'll realize is there's a very, very, very heavy geometric flavor here. The intuition is not just out of nowhere. It's not magic. There is an intuitive reason this formula we're going to write holds. Okay, so what this means is that we can do the following. We know the length of the curve is approximately the sum k goes from 1 to n of this sort of delta x quantity squared plus delta y quantity squared. Now, what the previous page showed us is if we can somehow get dy over dx, we can replace it with f, the function, a simpler expression of our function. And what this requires of us is this requires us to do a little bit of algebra. So this was going to require that instead of writing this thing in the square root the way we've written it, let's rewrite it. I am going to factor out a delta x. So I'll go slow. I'm going to take a delta x squared, and I'm going to pull it out of in the following way. So you're going to say, what in the world did you do? And I'm going to ask you to distribute through those braces, and you'll agree with me that the two lines are the same thing. Take that delta x quantity squared and run it back through. So you take it here and then take it over here. Okay, now, when you were in middle school, you learned properties of radicals. If you have a product inside, you can split it. Just like when you were a kid, you might have learned to write the square root of 8 as 2 root 2. I'm going to do the same idea. I am going to pull this delta x squared out of the radical. And when I pull it out, I have now made an awesome discovery, because now I have my Riemann sum. Because what's left inside the radical is just this. And then I have my delta x outside. This is what I wanted. But we have a better expression for delta y over delta x. Delta y over delta x is ugly. It's like f is value. It's a big, ugly difference quotient. But on the previous page, we showed you two ways, both theoretically with the mean value theorem, and we also showed you graphically so you have intuition. Now, just because I said we show it two ways doesn't mean it's obvious. It ain't easy to make sense of that. But I really hope you try. Because what this says is we can now write this like this. F prime evaluated at CK quantity squared delta x. This is a Riemann sum. And it explicitly tells us what the function is. Now, there's a whole lot of scary symbols on this whiteboard. I get that. But I'm telling you, it is worth the time and effort to try to understand this. You'll have a better appreciation for this class. You'll be better to gain things from this class. Again, I can't emphasize this enough. No one cares at the end of the day how quick you are at integrating. I showed you last class, we got software for that. What we don't have is software that can think like a human. So it's a good time right now for me to sort of digress into something that some of you may have heard me talk about before. But it dawned on me, I was listening to a podcast last week. So there's this famous physicist nerd who has these awesome podcasts. And last week, they're talking about autonomous vehicles. You know, like people, you know, you've seen some of these cars, they drive, you know, Volvo has them in Pittsburgh. You know, people think Tesla drives itself. It doesn't, right? But people, you know, think that. And one of the big issues with having a car that really doesn't need a human to drive it is that these machines can do lots and lots of stuff. If we engineer them and give them so much memory that they can tell most things, then these cars can pretty much behave without killing themselves, right? Or killing whoever's inside or people on the road. But what they can't do is they can't always recognize things that humans instinctively do. Like they might not recognize a snowman or the way you would recognize a snowman. They might not recognize a dog on the side of another vehicle, like a picture, as a picture on a car. And there's certain things that we can program computers to do. I mean, we can train computers to teach themselves chess and be better than any other chess player in the world. We still quite can't teach computers how to think using instincts that humans have. Now, maybe someday we will, but we ain't there yet. So we still need ideas, and we need you to be able to think in these ways, where we have now solved multiple different problems using the same theme. I mean, the end game, yeah, it's great that you can do integrals. It's great. Maybe you like integrals the way some people like to collect coins or the way some people like to paint or whatever. But being able to integrate is not a skill that is that important in 2020. The important skill is understanding when an integral is useful and how to build one. That is the skill. Now, that ain't an easy skill, but 10 years ago, it was important for you to integrate, and that wasn't an easy skill. Now the software makes that obsolete almost. Do we get this? All right. But if you like integrals, that's fun. Sometimes I solve integrals for fun too. It's great. It's a great challenge. We're going to teach you a bunch of ways in next week. But right now, we want you to understand determining when an integral can be used is extremely useful. And you guys will see this over and over again in other classes too, depending on your major. All right, great. So what does this mean? What this means is the following. That's our approximation. And so we can now define the length of a curve. So suppose f has a continuous derivative. And by the way, you need that continuous derivative nonsense for that argument to work. So suppose f has a continuous derivative on some interval a comma b. Then the length of the curve y equals f of x is L equals the integral from a to b of the square root of 1 plus the function's derivative, quantity squared, dx. Now, I could have come in here an hour ago and just said, here's the formula. But I don't feel like that's useful to you. I don't necessarily feel like it's useful to me. The important thing is, where does this formula come from and why is it true? And that's what I was trying to get you to understand and appreciate. It ain't going to happen overnight. None of you is going to go home and be able to replicate that in an hour. It's going to take a lot of effort if you want. And I'm not even saying you have to, but that's my advice. You might say screw it, which is fine. The first thing that you need to note, though, is this square root is outside of everything, which even from the little bit of integration you guys have done in your life, that should still be a red flag that most of these integrals are going to be very, very challenging. Because really, the only way to get rid of a square root or the only way a square root is not going to cause you an algebraic problem necessarily is if what inside is already a perfect square. Because then if it's a perfect square, somehow the square and the square root cancel each other out. And then if it's not a perfect square, you're going to have some useful substitution that works. And we're going to find that that's very rare. But let's do an easy example just to see how it works. And then there it is. Does anybody have a question, comment? Okay, so let's determine the length of y equals the square root of x on 0, 1. So just to get some geometric sort of flavor involved, not that you need to do this, but let's just draw the graph. So the square root function's graph looks like this. Yeah, that's bad. It's a little steeper than that. And so we're interested in what's happening on, say, 1, 1, or from 0 to 1. So you'd imagine this is the point 1, 1. So what is the length of this? So the first thing we need to do is note that y prime is the derivative of what? Well, we want to take the derivative of x squared. What's the derivative of x squared? Or excuse me, x to the 1/2. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. So that y prime quantity squared is 1/4 x to the negative 1. Or if you'd like, you can write this as 1/4x. So again, the derivative, don't get, so this is going to be an issue that's going to start messing with our brains because you guys have been integrating the last few, weeks in calculus, and you might forget derivatives. First thing we have to do is compute the derivative. So what's the derivative of x to the 1/2? It's 1/2 x to the negative 1/2. And when we square that, we get 1/4 x to the negative 1, or 1/4x. Okay, so then what we have is the length we're interested in is the integral from 0 to 1 of the square root of 1 plus 1/4x dx. Which we might want to try to rewrite for the sake of what we can do as, if I can combine everything in there, maybe I write this as 4x plus 1 divided by 4x dx. Okay, so here's the issue now. How can we compute this? can we? So again, what strategy might we try? And let's write it down one more time. It's the integral from 0 to 1 of 4x plus 1 over 4x dx. So this is something that is often tough for us when we're in Calculus 2 to appreciate. How would we integrate this? Can we integrate it? I mean, really, the only tricks we know are some algebra tricks and then a substitution. But is substitution going to help us here? What would you even try to substitute? Does anybody have any thoughts? Any hints? Or not hints, but anybody have any ideas? So let's remind ourselves so to use the fundamental theorem of calculus, we need to know the antiderivative of this scary function. And there's a couple other issues here that we haven't even mentioned. For example, 0 is not even in the domain of this function. Can you plug 0 into that function? No. You understand what I mean by that? So we don't even know if we can, you know, we're not sure what to do is what I'm saying. By the way, it's worth pointing out, and this is what will get you guys into trouble in some of your classes, there is a way you can figure this out. It's not an easy integral. You have to get very creative. But right now, what we need you to appreciate is we need you to appreciate that there is indeed an issue here. What is the antiderivative of this function? Because if we don't know the antiderivative, we can't do anything. Do we understand the problem we're having here? It's not an obvious thing to do. Zafalgar, you solved it. What is it? Don't just tell me it's 1.47. How did you do it? Right, so this thing is not an elementary integral. And what happens is many arc length integrals are not elementary. And so the reason I bring this up is because of what I said earlier, and that is very few integrals that we're going to encounter with particularly arc length are ones that we're going to be able to easily solve. In fact, they're usually quite difficult. Does anybody have a question? Comment? Turns out we're going to be able to do a little bit, but we'll come back to this guy in a little bit. And by the way, what Zafalgar is pointing out to is if I were to go to Wolfram, let's do this real quickly. If I went to Wolfram and I just say integrate, first off, if I say integrate this thing, so we got to be careful how we put it in. So what is this? This is square root, and then the numerator is 4x plus 1. Then we have to divide 4x. And if we put bounds in, what it's going to do is it's going to spit out a number, 1.47. So the first question is, how does it get that? Then the second question you ask, is that an exact answer? Is it an approximate answer? Now we're going to lean towards it's exact because Wolfram's usually very good. If it's approximating, they'll put an approximation symbol there. So first off, how did they get that? And you'll notice that unless you pay, they're not telling you anything. So maybe you want to know if Wolfram gets the antiderivative. And so if I just say integrate, it will give me the antiderivative if it exists, and it does. But look at this creature. And most of you don't even know what this tan h minus 1 even means. Now, that wouldn't stop some of you from putting that on the midterm if I put this problem on there. You just copy it off Wolfram like you knew what the hell you were doing. So when you asked the other day, Ethan, and I think a few of you asked, can we use this? Go ahead. But if you just write this down, you ain't getting any points unless you tell me what the hell it is, right? So anyhow, these are, this is a very sort of difficult integral in a sense. And what I'm trying to foreshadow towards is that there is so much we don't know about integration yet. We are only able to integrate so many things. And then just given something as simple, we think, as the square root, finding its length, we wouldn't think, since it's not an ugly looking function, it would be hard. Turns out it's hard. Try doing the same thing for x squared. So we're out of time. I can't do. We'll talk about this Thursday. But a similar thing, if I asked you to compute the arc length of x squared, you're going to arrive at a similar issue where you don't know how to integrate it. And so one of the things I asked you to do on the homework in those cases is use a Riemann sum to approximate. Anyhow, we'll talk more about that on Thursday, guys. Thank you. I didn't mean to keep you so long. We'll talk more about this Thursday. Thank you, guys. Take care. Go now in peace.